So I appreciate being here. Can you hear me okay back there? All right. So thank you for the great introduction. Our group at Colorado is a relatively large group. There is about half a dozen of us who do MEMS-related activities. Probably out of the entire graduate student body in mechanical engineering department, probably 25% or so are involved in microsystems, one way or the other. We have a lot of activity in my group. My group has 10 people in it, 2 postdocs. ALD seems to be one of the basic technologies that propagates through all the projects over the past decade in my group. So I wanted to focus my talk on ALD and its applications for MEMS and nanosystems. If you've never been to Boulder, Colorado, you should come visit us. There is a nice picture of Boulder, Colorado in the summertime. You probably cannot spot the university, but it is there somewhere.
It's beautiful.
It's beautiful year-round. The university is right there. And we do have snow-capped mountains year-round. Okay, I am also responsible for bringing the snow to you over the weekend. So. All right, so moving in on the presentation. So why are we interested in ALD? There are 2 really examples I wanted to emphasize here why ALD may be of interest to micro-nanosystems. Maybe start with actually the lower example for the batteries. ALD traditionally is used as a coating material, been used in dielectrics in semiconductor industry for a long time. More recently been used in battery applications. And so the example shown here is from Professor Si Lee's group at my department. He works on solid-state electrolyte batteries. And they use ALDs for coating nanoparticles to keep stability of the nanoparticles. And so the graph you see on top is sort of the discharge cycles here, typical cycles, and then once coated with ALD alumina, you can see this curve right here. So you get a better performance there. Another more recent example of ALD for standalone micro and nanosystem, or more nanosystem, is the ALD-based bolometer. This one is actually out of Tom Kenny's group at Stanford. And we do collaborate with that group. So I'm going to mention a few more things about this project. But what you're seeing here is a suspended plate or suspended membrane made out of platinum ALD. And the reason why you want to go to ALD in this is you want the thermal time constant to go way down for the bolometer performance, so you want ultra-thin film. And here the platinum itself is used as both the detector and temperature-sensitive resistor. So just a brief slide on ALD. People here know what this is, but just a quick review. So one nice thing about ALD is it allows a binary sequential reaction. And so in principle, at least in theory, one could build one atomic layer at a time. So you have perfect atomic control in thickness in vertical direction. Examples illustrated here is through the ALD alumina, which actually works quite well for theoretically you can get a very precise linear curve of thickness versus the number of reaction cycles. So traditionally, ALD has been used as coatings for thickness control, step coverage, conformal deposition, pinhole-free deposition. And it's extendable pretty much to any kind of substrate of any size, as long as you have reactor chamber big enough to handle it. It is compatible with MEMS materials, compatible with released MEMS devices. What I listed here are the materials we work with. University of Colorado. We collaborate with Professor Steve George in chemistry, who is well-known faculty in in this technology, in atomic layer deposition. So these are the materials he has in his lab. He uses mostly custom-made reactors. We do have a BENEX system that we recently just installed for larger substrates, but mostly we build custom-made reactors. Some of them are dedicated to my group specifically for tungsten deposition and aluminum oxide. Okay, so first I'd like to talk about more MEMS type of structures, and then the second part of the talk is on nanoscale systems. So the topics I'd like to cover, so this is sort of an overview of what we've been working on: microstructure adhesion, optical applications, wear-resistant coatings, creep control, and combination of organic, inorganic films. So first, the microstructure adhesion. We've been looking at this problem for a long, long time. In fact, the very first work we introduced to the MEMS community on ALD was for this application for adhesion control. So adhesion happens due to combination of three forces: capillary, electrostatic, and van der Waals forces. And you can design ALD-type coatings to control pretty much any of those or a combination. And so what you see in here is sort of a traditional way of looking at the beam adhesion. This is polysilicon suspended beam. And you can look at you can measure the adhesion of the beam relative to the substrate, the length of the adhesion. And so based on this equation, one can determine the adhesion energy. It doesn't tell you which force is involved, but at least it gives you adhesion energy. So using this, one can actually study how different films would behave. So here's an example of hydrophobic ALD coating that we did a while ago. This is DMA-based coating. The picture on top is the coating on aluminum oxide, and you can see the contact angle of 97 degrees of the water droplet. Functionalized coating like that can give you better contact angle, something over 100. But here's an example of interferometric measurement of an array of polysilicon beams coated with this hydrophobic coating. So here's an array of beams. Same beams here as shown right here. You can see these beams here all adhere to the substrate due to stiction. All of these beams are freestanding. Okay, so you can work on that direction of hydrophobic coatings. But also one can work on dielectric or semiconducting coatings to control charge between the surfaces. So here is an example of sort of an old device. This is a polysilicon beam made from MEMS process. And two examples of ALD-type coatings. One is aluminum oxide coating, and one is zinc oxide coating, both by ALD. If you look at the cross-section of this beam, you can clearly see the coatings. So it's a conformal process. Aluminum oxide here is used as a dielectric coating. Zinc oxide is more of a conductive coating. But what's interesting is actually when you combine zinc oxide and aluminum oxide. Okay, so you can make a super lattice. This is all done in the same reactor, actually. You can grow this kind of structures. You can do a coating layer of alumina, zinc oxide, alumina, zinc oxide, and so on. And depending on the thickness of individual layers and overall composition, you can actually control resistivity or conductivity depending on how much zinc you have in a composite. And it's very interesting because this one here is actually tunable 19 orders of magnitude of the conductivity. So you can make a coating that actually bleeds out the electrical charges, which would be an interesting application. Okay. Next one, speaking of super lattices, so this is some work from Steve George's group. On optical MEMS, this is coating for X-ray mirrors. Now the X-ray, of course, has to come at a specific angle for this to work as a mirror. But one can build a coating of layers, alternating layers of tungsten and alumina, as illustrated here. And so for for X-ray type application, of course, because the coatings are very thin. They wouldn't work for visible light, but they certainly work for X-ray or deep UV. All right. Also similar concept, aluminum oxide tungsten type coatings for wear resistant coatings. This is work done with Sandia. A while ago, they used to make these micro machines. And so that grind silicon and silicon basically wear themselves out. So you can coat it with ALD material and have an improved lifetime of the device. Now, one interesting application of this coating is also for creep control, stress control, relaxation in films. So here is an example of sort of a classical polysilicon beam coated with gold. And over time, the residual stresses are such that over time the beam curvature will change. Okay? If you coat it with ALD, encapsulated with this hard shell aluminum oxide, you can pretty much find a way how to control this over time. And so this is important for many applications. Here is a corner of this polysilicon beam just to show conformality. It's an important problem. It's a problem that people typically don't talk about, but it's there. So you need to figure out how to control it. So that's inorganic coatings. So one thing about inorganic coatings is that they are hard and brittle, but they're high modulus and high refractive index. So the other side of ALD is what's called molecular layer deposition, or MLD. And MLD produces organic coatings, which would be soft and flexible and low modulus. So that would be a different application, but then what you can also do, you can mix the two and actually tune the mechanical properties of the composite. So just as earlier examples of MLD coatings that we've been working on are the coating called alucone or metal cone in general. You can use different metals other than aluminum. And so this is sort of this organic molecule that's called ABC reaction rather than just A and B reaction based on ethanol amine. So this ABC system is also quite controllable. If you look at the measurement, it's linear growth with time. The nice thing about it is, again, a very low temperature deposition process. But it does produce coatings at a low density, low roughness. And the interesting thing, so you say, well, what's the first application of this? Well, the first application of this was we were using this as a sacrificial layer for making nanostructures. So what you see here is a very simple structure, is a tungsten beam suspended. This is done by ALD. And the gap here, this air gap, was actually the alucone MLD coating, which was removed in hydrochloric solution. And so now, once you realize that you can make this type of technology, then you can create sort of a custom-made surface micromachining process in-house that uses ALD for structural layers, not just coatings. And because you can make removable layers that are precisely controlled in thickness, you can make very, very small gaps. So this one was done with MLD, alucone. The other application of this is to make a flexible coating multi-layers. And so this is a structure, again, a lattice structure. What you see here is alumina, ALD, polymer MLD, alumina, polymer ALD. And so an example of this on pen substrate is shown here. Alumina, MLD, alucone, alumina, and this metal was used here for conductor. The nice thing about this, again, is you have a composite. You can look at it as a composite, and depending on individual thicknesses, of these layers, you can create something that has the mechanical properties that you're looking for. It could be a flexible, tough coating, could provide superior gas barrier diffusion, could be transparent interconnects, and so on. And so, speaking of transparent interconnects, so more recent work from CU Boulder would be zinc oxide or zinc-based MLD based on diacyl zinc. And with this type of material, you produce something instead of alucon, we could produce something called zincon. But once you mix it zincon with zinc oxide ALD, depending on the ratio of the two, one can actually tune the electrical properties of the coating. It is a transparent coating. It's a flexible coating. And the idea here behind this research is to find a replacement for ITO, for transparent electrodes. So here is more of a, on the same topic. The best coating that we get is this one right here, to the 2 ratio. You can see it's an order of magnitude off relative to ITO performance, but it's still pretty good. It's a transparent, tough coating, and pretty easy to deposit, in fact, and pattern into electrodes. So we are looking into this right now for flexible coatings. Now, the other thing with this type of coatings is you can tune the mechanical properties. And again, what you're seeing here is an example of aluminum oxide ALD and alucon MLD. And the mixture of the two, depending on how many layers and the thicknesses you have, the composite, you can actually tune the properties, the mechanical properties, as a function of the ratio of the two materials. Here is an example of the Young's modulus and the hardness. And so we do that through the sort of nano-indentation loading to extract the mechanical properties. Okay. Moving on to nanosystems, what I'd like to cover is sort of a mechanical properties issue and the freestanding nanostructures, and then some examples on carbon nanotube transistor work that we did in nanowire work. So one thing about mechanical properties, we really don't know what the mechanical properties of ALD films are. It's not something that's well known. We can easily measure electrical and optical properties, but mechanical properties are not characterized. Aluminum oxide is pretty much, but not much on anything else. So we have to come up with our own techniques to measure the mechanical properties, because if you do want to make freestanding structures, you have to know those. Without mechanical properties, you're just not going to be able to design anything. So we've been looking at different sort of, this is traditional techniques borrowed from MEMS community, pointers and freestanding beams and so on, trying to extract the residual stresses and Young's modulus and so on. So here is an example of where the mechanical properties matter. So maybe start actually in this corner right here. Here is an example of critical tensile strain of aluminum oxide film thickness. Okay, and you can see that the thinner the film gets, the higher is the critical strain, which is something you would expect. But still, how to model that at this nanoscale, we don't know. Okay. There are some ideas on that, some models we could apply, but this is not well understood problem. But here is more of a nanoscale or MEMS type of structure. So if we take a structure like this, and let's say we just want to make something that's flat on a post, okay? Here is where we started. It's a stack of aluminum oxide, tungsten, aluminum oxide, and it's a mirror. A very thin structure. Tungsten is in the middle. The reason why we use aluminum oxide on both sides is to prevent tungsten from oxidizing. Okay? But here is the problem. We don't know the properties of individual films. And so to go from something like this to something that looks like this, which is the same device, it only took about 80 hours of clean room work and only 2 to 3 nanometers variation in film thickness. And it would be very nice to know ahead of time what the residual stresses were, so we could design for it, because there is plenty of information how to design multi-layer structures based on residual stresses, but you have to know the stresses to begin with. And they are a function of film growth conditions, temperature, and rate. They also turn out to be a function of whatever the underlying substrate you were using before. Okay, so that's one issue that really needs to be worked on. Now, as far as examples of freestanding structures, so here's an example of some work on a deformable micromirror device. This device itself is ALD membrane, metallized, to make a deformable mirror. It's made on one substrate, and then it's flip chip transferred to another substrate above a set of electrodes. And this one actually had sort of this circular type electrodes. There is 5 of them. Depending on how the voltage is applied on individual electrodes, you can see the interference patterns of this device. Probably this one was the smallest pressure sensor we've ever made. This one is a very small diameter device. Here's the diameter of this in the order of 100 microns. This device was done in collaboration with ETH Zurich group, Christopher Harold's group. And what we did here, we used the ALD to make a membrane. And we used single wall carbon nanotube as piezoresistive sensor on top of the membrane. So as the membrane deflects, pulls on the nanotube and its properties change, piezoresistive properties. Some of the work on resonators, once you start making free suspended structures, you can easily make suspended beams and bridges that could be brought into resonance and make sensor-based devices like that, based on resonance. This one here is done with aluminum oxide. You can go and make nanoscale switches once you know how to make gaps. So again, everything here is made by ALD. This is a tungsten-based device. Here's a tungsten ALD switch, cantilever here, 1.3 micron long. The air gap was created by MLD. Here, this device is a 2-terminal device, its functionality, and this one is a 3-terminal device functionality. It's a molecular transistor.
So, Victor, what are some of the advantages in the quality factor that you get out of this?
A quality factor for the resonator?
Yes, yeah. In comparison to other processes.
The main advantage you get with ALD is you get ultra smooth surface.
Yeah.
So you get very, very low energy loss in the surface, because you get, well, I know Gary would disagree with me, but in principle, you get atomic scale control in thickness.
The Q is...
Right. The Q is very, very high. And your gaps, for the same reason, your gaps are precisely defined. So electrostatic gaps, for example. Okay. So the bolometer work, this is something we collaborating with a Stanford group on. This is ALD platinum device, just made out of platinum. The idea with this bolometer is that one has to get the thermal time constant down. So the smaller the mass, the smaller is the time constant, the better is the overall figure of merit. And so here the platinum is used both as a detector, as the membrane, as well as a piezo resistor.
Those are 2 tethers?
Yeah, those are 2 tethers right there. It's an interesting concept. So at Stanford, they use platinum. We use tungsten. Both devices work. They're both competitive against each other. they are better in platinum, we are better in tungsten deposition. But the same physical principles apply to shrinking this device down. Some of the work on carbon nanotubes, or ALD for nanomaterials. So we've done some work on coating the nanotubes with successive ALD films, and of course at this scale, surface is everything. Shown in this diagram, but I don't have to teach it to this class. You can see here, this is a carbon nanotube, successive layers of alumina, tungsten, alumina. If you could be very clever and knew how to do it, you could make a world's smallest coax cable. The cartoon works, at least. So, but here is what you can really do with nanotubes. So this is more recent work. This is aluminum glycerol, MLD, based reactions on a nanotube forest. And what you see in here, let's see. So this is the material itself. This is reverse. This is material itself without coating. This is material with coating. The amount of coating is 10 nanometers MLD. You take a close look at this, see how wonderful the process is. Not only it interlocks individual nanotubes when they cross, but it actually permeates into the actual fiber. So we're looking at this type of materials right now to see what we can do with them, how we can enhance the properties of the carbon nanotube materials with this. The other thing to see here, this is MLD. Look how conformal the coating is on carbon. There is no pretreatment of any kind here. MLD just happens to work on carbon nice and smooth. Try to do aluminum oxide, you do have to do nitrogen treatment of that first. And aluminum oxide actually nucleates somewhat in droplets first before you get enough thickness for the layer to take hold. So one thing we've been looking at for ALD for carbon nanotube devices is this one for carbon nanotube transistor. Again, this is work is collaboration with ETH group. What we've done here, this is very simple. In fact, they make the transistor, the carbon nanotube transistor, which are the contacts in this transistor degrade pretty quick over time. So if you look at these curves, yeah. So the black curve is what you see in here is the current versus voltage for this FET. This is 6 days. After 6 days, you can see how much shift you get. Okay, the device is totally unstable after a few days. Now, if you coat it with ALD, the contacts, you stop oxygen diffusion into contact or moisture. And so what happens now, the red curve is after 100 days. And so the device actually turns out to be much more stable over time. So maybe it's a technique for encapsulating nano-scale type of devices. So the other example I wanted to bring up is the nanomechanical resonator. So we've done quite a bit of work over the years with NIST Boulder group. They do MBE growth of gallium nitride nanowires. Their interest has been in LEDs, photonics applications for this type of nanowires. And we've been working with them in that direction as well, but we also looked at individual nanowires as resonators, as mechanical resonators. And so, well, just a few photographs here. So here's what these nanowires look like, typical structure for gallium nitride crystal. You get a forest of this type of nanowires. And here's an example of individual nanowire resonances. So this is device without resonance, and then you can oscillate in this mode or this mode. So what we've done with ALD is actually we would coat the device with a conformal coating. And by doing that, we would tune the resonant frequency. And so you can shift the resonant frequency based on how much film you put in. The interesting thing is that chemically, if you remove the film, it actually goes back to where it was. So there is really no damage to the actual device itself. The other thing that it actually shows is this makes a very sensitive thickness monitor. And so this in itself, you can put this in the ALD chamber, and you can measure the how much you deposit of ALD film. Sort of replaces your quartz crystal microbalance with a nanowire sensor. So one more slide before closing this. So the other work that we are looking at is can you do concentric sort of electrodes on the nanowires? And this is a lot more challenging than one would think, but you can. And so what it shows here is nanowire coated with aluminum first, and then tungsten. And you put a layer of photoresist, and you can thin it down, and you can selectively actually remove the coating. Or you can under-edge the coating and make sort of a hollow shell around the nanowire for electrodes. Or you can do something that kind of goes the other way around and deposit some mass on top versus the bottom. So depending on the application, this would be more for resonator type applications. This would be more for making concentric electrodes around the nanowire for photovoltaic applications. So if you try to make an LED out of this device, you need somehow to bring electrodes around it. And this would be a technique to making this happen. So give you a quick summary of sort of what we've been doing, what we've been working on. So electrical conductivity is an obvious thing here, controlling resistivity to avoid charge accumulation, isolation, improvement, interconnects. Mechanical properties, this becoming to be a major problem for my group. Actually, as we move more and more towards nano applications, we are developing programming sort of a reliable way of extracting mechanical properties of this type of films. Inorganic as polymer type of composites, this is a very promising application for a lot of stuff that we're trying to do, especially as we move to flexible substrates. Okay, and then nanomaterial coatings and contacts, again for gallium nitride nanowires or any type of nanotube type of structures. And then nano-scale freestanding instruction transducer. This is a very interesting one. There's only a few examples where this kind of emerged so far. Maybe switches or resonators or bolometers. It would be interesting to see what people can come up with at that scale. Obviously, optics benefit significantly, but you have to be at the right wavelengths for this to happen. Okay, so with that, maybe acknowledgments. So Professor Stephen George been my collaborator for the past 12 years in this field. So without him, probably ALD would not be happening in my group. Or we'll buy commercial reactors and be very limited. It's nice to have somebody next door who can build whatever reactor you want for whatever chemistry. And if it blows up, he takes the blame. Okay, my students, there is probably a dozen students or so who contributed to this slide. And all the work I've shown, and actually in these slides, have come from DARPA support. We had a center that recently graduated, this center called IMINT, that was around for 5 or 6 years, and was a lot of support. The pictures on top are Boulder Creek, our major river. Summertime and wintertime, same shot. So, all right, thank you.
Okay, questions, please.
Yeah, couple of, do you ever look for texture in the ALD films, or is there ever an application that you think about for the other one? For battery use, is it production or research? Is it at which stage is it at?
So for batteries, definitely research at this point. Texture, can you be more specific with your question?
Would you like to have some kind of crystalline structure in the ALD film for any application or are people actually working on that material where making some progress?
Okay, so there are several ways to answer that. Okay, crystalline, we don't really look for it, but it's becoming a problem for us. Okay, for example, the aluminum oxide is not crystalline here. It's more like amorphous material. Zinc oxide is crystalline. Tungsten is crystalline, and platinum would be. Although we don't work with platinum, so I'm not as familiar with it. But tungsten, because of the film thickness, because it's so thin, the polycrystals are becoming an issue for us electrically, as well as when it comes to thermal conductivity. So, for example, we try to make a bolometer out of tungsten, and the thermal properties of the material are totally not what we expect it to be. Okay, and it all has to do with the polycrystalline structure. So I don't think I answered your question directly in terms of surface roughness or anything, but we are concerned about the structure of the material, of course. And so that's another issue that, the properties are not what you would predict. And certainly no one knows what they are at that scale.
And not what you prefer either, I guess.
No. So it's full of surprises.
Yes.
So the use of the ALD layers on battery materials has been quite convincing for those kinds of battery electrodes that are essentially powders that are pressed together.
That's, yeah.
The ALD maybe does many things, I don't know. Certainly, as you showed with the wires, crossing wires get welded together, stability changes and so on. And then on these battery materials, we have these SEI layers that form and so on. We've done some looking at exactly the same kind of thing on well-defined nanowires with much less convincing results about the ALD benefit. Do you know of any nanowire work that's been done to complement the micro or nanoparticle?
So the only work I'm familiar with would be the nanotubes, carbon nanotubes, or nanoparticles for, not just for batteries. So ALD and nanoparticles is used for variety, for electrochemical reactions, and cosmetics. Yeah, I'm not familiar with nanowire work per se.
So can you elaborate a little bit more on this freestanding structures and areas that we have not yet explored using ALD process? Where do you think the field would be going toward by using this technology, especially maybe structures that are out of plane and applications that will require this?
So the bolometer is actually an excellent example that uniquely benefits from ALD film because of the thermal isolation. I think there is a huge field in optics, freestanding films like that, because you have unique thickness control. The question is how to do lateral control other than just E-beam. My understanding is there is a way you can do ALD control laterally. And people demonstrated there have been a few papers published on laser control of ALD. You activate the substrate laterally along the substrate. So instead of just doing vertical control, and then have uniform blanketing of the substrate, activate the substrate at specific location such that you only grow the film in so you don't have to do post-lithography. Okay, so no, you don't.
So it's selective.
Selective ALD. Okay, and whether you do that with maybe some nozzles, a nano-scale, or you do that with lasers or something, I think that would allow unique fabrication capability of making nanoscale gratings of structures. Okay, so it's not necessarily that you can make really robust devices that are suspended, but I think gap control is very critical. Certainly MEMS field benefits from that, as well as maybe optics.
Another question is, so in the NEMS field, are there applications that actually have made it to manufacturing yet?
No, not yet.
Or any are likely to?
Not yet, but it's becoming to be more and more popular. I would say reading the abstracts for transducers,
Yeah.
that's upcoming. I would say you probably see a quarter of the papers that use ALD somehow.
Quarter of the papers?
Yeah, it's linearly going up. It's more and more, especially in Asia.
Yeah, I was amazed myself how it's becoming to be a sort of a normal tool in any micro-nano lab.
Well, Qualcomm uses this quite a bit. I mean, that's one example of the manufacturing. But they do it in Taiwan, and the development of the process is done here, but the manufacturing is done
But they're using it for what application?
for coating.
For coding.
Just
Coating.
passivation.
Yes, for coating of for the optical device, and they use ALD. Yeah.
So you talked about composite ALD materials by using multiple layers of inorganic and organic. ALD, does addition become a problem between these layers? And also, what would you think about the final conformality of the composite layer? The different inorganic, how does the final conformality look like?
Well, the layers are conformal to each other. The topography of the underlying substrate would be less and less of a problem as you keep depositing more and more layers. Okay, intuitively that kind of makes sense, right? As you keep depositing more and more layers, whatever the issues you had with topography would be gradually reduced. Adhesion between individual layers. I think I don't know the answer on that one. I mean, most of these layers are covalently bonded, so they're pretty strong adhesion.
About MLD, it seems like this is a way to use some interesting polymer coatings. Is there anything like everybody's like really familiar with that can be deposited by, I don't know, like, I don't know, polystyrene or is that possible?
So I'm really not an expert in that. The MLD films, so the alucone-based or the original MLD film is more of like a nylon type of material. The zincones, I'm not sure what exactly they are. But one thing you're right is that for flexible substrates, as a barrier coating, it works extremely well, but not by itself. It works as a superlattice of organic, inorganic. You can do, there has been some nice work published on that, in fact, by Steve George's group, where they show improvements of barrier coatings like that on the order of 3 orders of magnitude for water permeation, just by doing multi-layers of MLD and ALD alumina. So it works extremely well, plus it becomes tough and flexible, so it doesn't crack.
So this Q factor, 50,000 on the cantilever is very nice. Do you yet know about the Q factor on those nanowire resonators that you presented on the last couple of slides there?
These ones? Let's see. I'm trying to remember what the Q was. No, that's not an gallium nitride. The gallium nitride ones should be.
But actually, is this correct? 10,000 to 100,000?
Yes, that is actually correct.
And so on these nano-scale resonators, so of course the cantilevers are horribly damped in viscous solutions. Do you know about how badly the Q factor suffers in viscous
In these devices?
Is this something that you absolutely must do in a vacuum, or you know?
These are done in vacuum. These are measured in vacuum. Yeah, I wouldn't know what they would look like in ambient. 100,000 is not that unusual for this type of a. I mean, this is a single crystal gallium nitride. The nice thing about this process, they're grown by MBE, so they are defect-free. They're C-axis, so they're pretty high quality to begin with. The other nice thing about gallium nitride, it really doesn't oxidize and doesn't contaminate. So you can really make very nice devices with this type of nanowires. Yeah.
Any more questions for our speaker? All right, let's thank him for that very informative.
Okay.